Welcome. Today is Wednesday, February 12th, 2025, and I'm pleased to welcome Chris Scotese to join us today to talk about all of his work on the Earth's past. And to start, Chris, if you could just summarize a bit about your past. You were just telling us, what was your PhD thesis in?
I was started as a paleontologist, and I was in a group of paleontologists at the University of Chicago. And we were in a group that we were trying to reconstruct the world through time. And it was clear that we needed somebody in the group who was willing to try to become a geophysicist, in particular, learn paleomagnetism. So my thesis was actually on using paleomagnetic data to orient the Pangea supercontinent and just learning how to do that so I could evaluate, so we could evaluate published paleomagnetic data. Then I went on to a postdoc at University of Texas in Austin, joined a marine geophysical group where at that time they were mapping the ocean floor. And so I've synthesized the ocean floor data so that I could use it to reconstruct the ocean basins. And then I went to work for Shell for a couple of years because they were very interested in my work because the oil companies need to understand the geology and the geography of the ancient world to look for oil. But I didn't like having a boss, so I finally became a professor at the University of Texas at Arlington, and taught Earth history, taught paleoclimate, taught a variety of other courses. Uh, and I'm now retired adjunct professor at Northwestern and working on a book to summarize and synthesize what I've learned. Uh, Looked at paleoclimate for a long time. And then obviously a natural spin-off is, well, if that was climate of the past, what's the climate of the future going to be? So I sat down a couple of years ago and wrote a carbon balance model to try to predict and try to understand how much CO2 or how much carbon we're putting in the atmosphere and use that to predict possible future temperature changes. So I'm here today to talk mostly about paleoclimate, but I'll start off with my insights and prejudices into what our current situation is in terms of global warming.
Sure. Have you taught a bunch of classes as well?
Yeah, I taught well, when you're a professor, you get to teach lots of different things, and I always use it as an excuse to learn new things. So the students were sometimes guinea pigs, but I've taught several seminars on particularly on future global climate change. Let's put it that way.
Mhm.
Uh, and there's one paper that if you haven't seen, was published in 2021. It was one of my COVID papers where I summarized climate change over the last 540 million years. And there's a fairly large section on future climate change.
Oh, okay, take it away.
Okay, well, first of all, I like to keep this very informal. I don't want to be a lecture, and feel free to interrupt with questions, though I will save some time at the end, especially if something isn't clear. Um, and so I'd like to share my screen, so I'm going to try to do that. And let's see if I have, here we go, share. Okay, you should be seeing my screen now.
Yeah, that looks good.
And so I'll bring up I have
Yeah, we
a
can see.
PDF with a bunch of slides, so to speak. So again, I'll start with the present and sort of work back and talk a little bit about the Earth's past climate. But this is a curve you're all familiar with. It's the global average temperature during the last century and a half. And this data basically is the basis for our understanding of climate change and future climate change, especially the last 60 years with this rapid increase. This is okay. I prefer to look at this sort of curve, which is a curve that shows the annual temperature changes for where I live, Chicago. Uh, so it incorporates a lot of the things that we experience which is has to do with daily temperature changes. You can see the seasonal changes, uh, the periods when it's cold and warm, and there's a 8-degree difference just in an annual cycle. So we experience a tremendous amount of temperature change just going through the year. And I've listed some of the average temperatures. Uh, the uh, what What's interesting, of course, is this gray area. This gray area is just a superposition of all the temperature measurements, and there's you can clearly see there's been a 0.2 degree increase, uh, and it's 0.2 degrees per decade. So if we started out in 1980 with an average temperature of 14, and I'm going now to a global temperature, the in basically 4 decades, basically we increase 5 decades we increased 1 degree. Uh, so we can do a very simple exercise. We can say, well, if this is what's happened in the last 40 years or so, what if we project it into the future? And so 2050 is basically 3 decades from now. So the temperature will increase by 0.6 degrees from 0.15, and then we can take it every 50 million years, 50 years, sorry, I'm thinking as a geologist, uh, and get sort of a projection of if this is business as usual, if nothing changes, uh, if whatever's causing the temperature to rise continues at the same rate, then we'll get up to about 19.6 by 2250, which may seem like a long time in the future, but from a geological point of view, it's sort of like instantaneous. So that's a rather uh, remarkable increase, just projecting present day rates of increase. Um, Now, the obviously groups like the IPCC have been trying to predict how that will actually happen. So here's a historical curve we just looked at. And then, if you have different scenarios, and I guess I should say the basis for the temperature increase is assumed to be CO2. And I'll come back to that when I talk about the paleoclimatic evidence for climate change. Um, but we can think of this as if what we're doing right now doesn't change, we're on this, whatever it is, this curve. If we make it, if things get worse or things get better. And then, as I mentioned, I built a little carbon model, and this was the curve that I came up with. Uh, and so it doesn't go up forever because what controls the driving force of CO2 are emissions and population. So this is roughly represents the population curve, the best guess for population curve. And I'm happy to share this work with you. I won't go through it in great detail now, but it's again, I wanted to know what is causing climate change, and in more particular, what would be a reasonable prediction for future global warming. So I built a carbon budget model that took into account things like population, uh, and so the number of people is obviously a first order effect, but how much energy each person uses is also very important. And as the third world develops, that that carbon footprint increases. And then if we're looking at if the CO2 is driving all of this, then obviously the energy mix is very important. So how much of our energy comes from fossil fuels, which is the oil, gas, coal, and then also we get some from hydroelectric and nuclear. And we're trying to offset some of these with renewable sources. Anyway, so this graph takes into account this sort of very basic energy balance. Uh, can factor in if we remove CO2, how would that affect things? We can factor in how much is removed naturally by nature. And I use the percentage that 45% of what we put in the atmosphere is removed by nature or returned to the earth in some fashion. Anyway, if you play, this is just an Excel spreadsheet. If you can play with the numbers, you can try different scenarios, and it generates a series of curves. Uh, the purple curve is just if things continue as they are now, very simple-minded, and the other curves are other predictions. And the difference between the green curve, which is a low temperature, this is temperature on the vertical axis here, this is time up to 2300, 2300, depends on how effective CO2 is as a warming agent. If it's not very effective, then there won't be much of a temperature rise. If it's very effective, there will be a dramatic temperature rise. So it gives a range of the possible outcomes based on the how effective carbon dioxide is. And then all the mathematics is over here. It's pretty simple algebra. And again, I'll send David a copy of the paper that describes this and the spreadsheet. If you want to play with it, he can pass it out to whoever asks him for a copy.
Thank you.
Also, I've made a copy of all the slides in this talk, and another little short paper I've written that David has that he can send out to people who are in attendance or interested. Okay, so that's the present day and the future, and I'm happy to go back and answer questions about this, but my real interest is the past. And so maybe I should stop. And is there a quick question about this
We see
material?
lots of stuff about the future. We're very interested in the past.
Okay. The so again, to understand how the Earth has evolved, I wanted to put together a curve that illustrated global average temperature. So global average temperature is a very general sort of description of how the Earth's climate has changed. From global average temperature, you can tell when times are cold, like the present day. We are in what I would call an ice house. And that's distinguished from times in the past when temperatures were much warmer. And so these are various periods where the Earth's temperature has been warm enough to be classified as a hothouse. And so I tried to identify the major events like the late Cenozoic ice age. You can see there's also a major ice age back here in the Carboniferous and Permian. There was a short little ice age down here about 445 million years ago. And the black line is the average temperature, and then the gray lines here are the swings in temperature due to Milankovitch forcing. In other words, the Earth's orbit changes, the tilt of the axes change, and that sort of all modulates the Earth's temperature. They're usually more pronounced during ice ages because a little bit of warming can melt a lot of ice, whereas a little bit of warming during a hothouse doesn't really contribute much to the situation. And then what I tried to do is divide it into sort of alternating periods of warmer versus cooler. One of the sort of interesting events which shows up, and it's highly exaggerated, is this dip right here. And that's at the boundary between the Cretaceous and Paleogene. And that's basically the extinction of the dinosaurs. The dinosaurs went extinct, we think, because there was a massive cooling event, essentially an impact winter, sort of like a nuclear winter where the particulate matter blocked the sun, which collapsed the food chain, which killed the dinosaurs and a lot of other things that were alive at that time. But so that was sort of an exceptional event. Whereas these other changes are due to subtle shifts in paleogeography and volcanic activity, maybe ice ages, maybe related to impacts. And so basically I want to tell the story of what's causing these changes back through time. Now, the other thing that you may note on this curve, we're down in this ice age, at least we were 10,000 years ago, and the current average temperature of the Earth is about 14 and a half or 15. So we've popped up from about 11 or 12 up to about 15. And my projection for future global warming puts us at the red star. So that's what I call the post-anthropic warming, or the warming for short. Now, the interesting thing about this rapid increase in temperature is that it's still relatively mild compared to the peaks of the past. We're not approaching anywhere near some of the great hothouses of the Cretaceous. or even this is the biggest peak, the highest peak. This is about 250 years ago, 250 million years ago, and that's between the Permian and Triassic periods, and that was the greatest extinction event of all time. 99% of everything that was on the planet got wiped out, and basically life had to re-evolve into all these empty niches. Uh, so I'm sort of, I consider myself a global warming moderate in that I think the word climate crisis and existential risk are huge exaggerations. And that's because of my perspective as a geologist is that it's going to get warmer, and but where we're going to end up, at least in the next several hundred or thousand years, is not anything uh, that would make us worry about the life on Earth or the human race getting wiped out. And I think that's an unfortunate hyperbola. Uh, the one thing that is true is that it is a rapid increase, so that anytime you have change, that's one thing, but how fast the change occurs is also important, and that adds additional stress to the people that have to undergo that change or survive that change. But I'm in favor of putting our resources to moderating and minimizing the damage done by global warming. I'm absolutely opposed to any attempt to stop global warming. I think that would be a waste of resources. And uh, I think we have time to adapt to whatever changes that are happening. But it'll be tougher for some people. Be tougher for people near the coast because sea level will rise a little bit, maybe a meter in a couple hundred years. It'll be difficult for people who experience severe storms or weather extremes. Uh, and so we have to pay attention to those areas. My rule of thumb is that if you live above 40 degrees latitude, you will experience a net benefit from global warming. Whereas if you live between 40 degrees and the equator, it'll be a very stressful time.
Can
Uh,
I ask Chris about
sure.
the past? Oh, you've done a lot of work on ice ball Earth,
Snowblowers,
ice,
right? Yeah.
ice snowball Earth, and you even made a video showing the gradients. So I don't know if you have any of those, but if you could walk us through, first of all, how many snowball, ice ball events have there been? What does it really look like? Is it like frozen at the equator? And how did it happen? And how do we know? And what are the uncertainties around these?
Okay, I have a slide later on that shows the snowball Earth in the context of other. But it's only happened. It's only happened really once. Uh, the This is an older graph, but you can sort of see there was a period where the temperature was very low. Uh,
This is 750 million years ago.
yeah, between 750 and 600, there were three major episodes during that
Hmm.
time. Um, and this was incorrect. The temperatures actually were much colder.
How do
But
we know?
well, uh, it's geological evidence for the most part. The the fellow who did most of the work on this is a fellow named Paul Hoffman, and he discovered he was working in Africa, and he discovered in Namibia a very unique rock layer, which was a solid crystals of calcite. Uh, so it was basically usually rocks are made of particles or animal debris, and but this was a crystallized layer of calcium carbonate uh, at a time when there wasn't much life in the oceans. So that was part of the reason. But it was something that was just completely strange. I mean, had normal rock layers above and below it. Then you had this crystal layer, um, and I'll think of the name in a second. But anyway, what it was all the crystallized CO2 that had been trapped in the ocean. Because if you have an ice layer covering the ocean, volcanoes are still going to erupt in the ocean bed. And so the ocean will become essentially carbonated. And eventually the carbonation or the calcium carbonate will crystallize out of the ocean water. And because the ocean becomes saturated. And so and these layers are synchronous all over the globe. And so that was, I think, one of the main lines. I was kind of a skeptic for a while, um, but I became convinced after I began to look at other evidence. The other evidence, of course, is that when you have an ice age, you have glacial deposits, and at the surface, there's I mean, usually you get glacial deposits near the poles, and so that I think the next slide. Well, no, let me go ahead. So this is the evidence for glacial for ice house. So if you have a hot house world, the opposite is an ice house world, and these peaks are times when there are abundant glacial deposits, and the number of deposits is down here, so you can sort of see how it changes. Obviously, we the best records for the recent, and uh, and by monitoring the temperature of the Earth, we can make a prediction whether there should be large ice caps or no ice caps. And when the Earth gets cool enough, then obviously the ice caps can grow, but they usually don't grow below 60 degrees latitude. Uh, but during snowball Earth, they were everywhere. So if we put the continents back where they were, we have glacial deposits at the equator. So
So does that mean that the entire surface was just white, frozen? There was
yeah,
nothing
well,
spare?
there's two theories. There's one called snowball Earth, in which that's exactly the case. There was a hard shell of ice, and the Earth was completely frozen. And the thing about the snowball Earth, if you watch my video, I make a point that once the ice, once as the Earth cools and the ice advances towards the equator, once it gets to 30 degrees, because ice is white and reflected, more energy is reflected back into space than is absorbed, and so that creates a rapid freezing of the rest of the surface of the Earth. Uh, and The other important thing is it's just a number, but uh, when it's Fahrenheit 13 degrees, which it gets to in Chicago every once in a while during the winter, uh, if it stayed that temperature, the ice would not melt, even during the summer, even with the summer sun. Uh, so that we know that at the equator, the temperature was minus 10 degrees on average during the year. Uh, but
And was this driven by Milankovitch, or because if you go, yeah, if you look here, go back to your first slide. If you know the first, yes. So if you kind of squint and look at a resolution of every 10 million years or so, you kind of see these waves that Nir Shaviv talks about the Earth going, or the solar system going up and down through the galactic plane. Can you address what would cause these super deep ice chasms? Can't be just Milankovitch.
yeah, I guess, well, there's two things you're addressing. One is it seems to be there's some periodicity. Okay. And I actually tried to figure out try to fit a periodic curve to this. And it turns out that these peaks on average are about 33, 35 million years apart. And of course, there's exceptions. Uh, but there looks like a rhythm. And that's what Nur's, one of his claims to fame is that he explains this as the Earth going through the galaxy's dusty plane, so it gets cooler. Uh, but the but that's sort of like Milankovitch, but only on a much larger scale. It's extra solar system effect. Uh, Frankly, we don't know why the snowball Earth occurred. What was the driving reason?
Ah,
Uh, I assume that what was different back then was there was no life, or very primitive life. There was no erosion on the surface. It was basically a lifeless planet except for the oceans. And even in the oceans, the creatures were very weird, uh, sort of like balloon animals called the Ediacarofauna. Um, so, you know, you can speculate, but we don't have a good explanation for the ice house Earth. Uh, but that's
and then what
sometimes
about the later ones at 450 or 300 million? We did have plant growth then.
Yeah, so these you can explain by looking at the Earth system. Okay. Now, by the Earth system, I mean the interaction of the oceans, the atmosphere, the cryosphere, biosphere, even plate tectonics. Uh, and It's like having a house instead of with one thermostat, you have a house with a dozen thermostats. And so you can fiddle with each thermostat. Each one makes the house warmer or cooler. And most of the time, it's fairly pleasant. Or most of the time, the thermostat's set above warm. But every once in a while, all the thermostats get set lower. And I have a diagram that shows that. Actually, this is just another version of that curve that shows in color what the pole to equator gradients were like. So the colors are temperatures at different latitudes, and the blue colors are the times when there was ice uh, at high latitudes near the pole. And you can see the ice didn't got down to about 60 degrees at most. Uh, we saw that one. And then this is one we can come back to, but uh, I was curious as to, again, what is driving climate through time. So people have published curves that are the data set. These are the CO2 measurements of CO2 in the past. And some of my early temperature curves did not agree with the CO2 curve. So people made a lot about the fact that, well, the temperature is changing, but it doesn't agree with the CO2. So that was 20 years ago. So I went back, now that I had a more detailed curve, I went back to the CO2 data. And my impression is that it generally does agree. CO2 generally does agree with the temperature curve. Um, the red curve was published by a guy named Gavin Foster, and basically this red curve is just an average location of all the dots. So you can see sometimes there's a good fit between the red curve and the dots, and other times there's not because there's some low dots and some high dots, so the curve goes between them. So I decided that instead of accepting all the data at equal values, to say, well, it can't be both. So if this is a warm period, then this is probably the data that I would believe. So for some periods where there was either no data or where the data were in conflict, I used the temperature curve to guide the way I drew the CO2 curve.
Let me ask you about temperature. Because you're most famous for the top graph, the temperature over time. First of all, how do you figure out where the land was 2 billion and 1 billion and 500 million years ago? How do you solve that puzzle? Because you don't get yet you don't have a time machine, and how do you know what the temperatures were?
Yeah, well, basically, again, I was trained in this thing called paleomagnetism. In paleomagnetism, you go out and you sample rocks because the rocks often retain the original magnetic field from that time period. Now, the magnetic field we know points north and south, but it also dips. The magnetic field is a dipole, so it comes out of the South Pole, it is flat at the equator, then dips back at the North Pole. Uh, and if you measure that dip, you can tell what latitude the rock formed at. And so that's one way you can know where the continents were. You can reconstruct their latitude. We can use that data back 1 billion years or more. There's paleomagnetic data that helps us determine the latitudinal position of the continents. For more recent times, it's even easier because we have seafloor spreading, and we can date the age of the spreading when the rocks were created at a mid-ocean ridge. And we can measure how far apart they move and how fast they move. And all the animations that I've made produced that or shown on my website, use that information. Uh, Now that's the position of the continents, which gives you some idea of the temperature because it's going to be warmer if they're near the equator. They're going to be cooler if they're near the poles. But the actual temperature is determined by. Um, uh, I take two approaches. One is I look at the rocks. If I see a tillite, okay, that's telling me we have temperatures around freezing. If I see rocks that are formed in warm environments like carbonates, like the Bahamas are a big carbonate platform, or salt deposits indicate there's net evaporation, which means it's hotter than it is rainier. Uh, the rocks tell you what the environment is like. And there was a fellow named Keppen who figured out how to map modern Earth in terms of climatic zones. So there are five major climatic zones. There's the equatorial, where it's always wet and hot, and then there's the arid belt, where it's hot but dry. And there's a warm temperate, where it's sometimes warm and a little bit cool, but generally a nice place to live. And then you get the cool temperate belt where I live, and then the polar belt. So if we use the rocks, we can map these ancient belts. And so that gives us an idea of the overall temperature of the Earth, whether we're in an ice house or a hot house. But if we want to stick a number on it, we have to go to oxygen isotope measurements from the tropics in particular. Animals use two different isotopes of oxygen depending on the temperature. So if you measure the ratio of those isotopes, you can determine the temperature at which the shell was made. And so people have spent their life compiling this data and coming up with a temperature curve. So the ups and downs here are from the oxygen isotope, and the dotted curve is sort of what the rocks tell us. Are we in a cold period or a warm period? A cold period or warm period? So that's in a nutshell, but it's all described in my paper if you
What
want.
about the uncertainties going back, the farther you go back? It must be pretty difficult to
Yeah,
figure out the
you
shapes
can't.
and the locations of the land areas a couple
Yeah,
hundred million years ago.
yeah. It's a. I have a curve that shows the uncertainties. My estimate of how well we know things. It's a exponential curve. It sort of increases not gradually, but rather rapidly. Uh, and some things help us out. If the continents are dispersed in many different places, it is harder. But if we have a Pangea where the continents are all together in one place, it makes it simple because if we just get the location of Pangea right, even though we don't know data everywhere, it makes a prediction for all the areas because they're all connected. Uh, Once we get back, and the other thing is fossils. To do this well, we have to know the age of the rocks. To know the age of the rocks, we have to have fossils. And fossils, of course, don't exist beyond 540. That's why this curve ends at 540. Uh,
Mhm.
I've recently put together a curve going back to 1,000 that includes the snowball Earth times, uh,
Mhm.
but it's very generalized. We don't have anywhere near this sort of detail. Uh, so I don't have that slide here, but I can send you a copy of that uncertainty slide. But I would say for this time, back to 200, we're doing great. Back to 300, we're doing pretty good. And then things become more dicey between 300 and 540. And there's a lot of debate about whether this was a really severe hothouse or whether it was more like I show it, something similar to the later time periods. Um, the But again, it's an integrated story. So it's not just temperature, but temperature affecting life, affecting the rock type. So when you paint the big picture, you have to paint a picture that is consistent with all the data, and that's the power of a multidisciplinary, multi-synthetic approach.
I guess though the plates themselves changed quite a bit. The plates we know today didn't exist 200 million years ago.
Well, plates come and go. That's true. New plates, like 200 million years ago, are about right about here. Uh, there was one big continent, Pangea, so that all the continents were on one plate. The oceans, there were different plates. We really don't know what they are because they've been removed by subduction. And then, of course, Pangea broke apart into the modern continents, the modern plates: North America, Africa, South America, Australia, and Asia. Um, and plates come together. India was once a separate plate, but it collided. But mapping those sort of changes out are not that difficult because record, we still have ocean floor from the time that the plates formed. Uh,
Mhm.
and
You
again,
can actually see the track of India going from Antarctica to Asia.
pretty much, yeah. Uh, Everything in the Indian Ocean, those large fracture zones, there's one feature called the 90 East Ridge, which is to the south and east of India. It goes all the way down to the ridge. And it was created by a hotspot, much like Hawaii was created by a hotspot, by a plate moving over a hotspot. The 90 East Ridge was created as the Indian plate moved north, and it generated a series of islands and volcanoes, and the and that trajectory shows precisely how India moved. So it's a recording of India's northward motion.
All
So
right, I have lots more questions. I'm sure other people do. Let me ask you about CO2. There are four major CO2 reconstructions of the past. They're all different.
well, I
Which
think I'm not sure what you're referring to. This the Foster one. Uh,
Foster, Geocarb,
okay, geocarb is a model. It's not based on data, uh, but
okay.
it's a reasonable model. It's a little bit old. It's like 30
So
years.
which ones do you like and which ones do you don't like and why?
Okay, well, there's a group now being headed by a woman scientist at Vermont, Barbara Hornish, and she recently published a paper on the CO2 record for the Cenozoic, which is this part of the curve here. And she collected 100 scientists who know about CO2 data from the Cenozoic, and they all evaluated each data point, and they came up with a new CO2 curve. So for this time period, that's absolutely the best curve uh, for CO2.
And what's that called?
Uh, let's see. I'll have to send you the reference. Basically, her name is Honisch with a double dot over the O,
Uh-huh.
and she's at Vermont. It might be HOR. I don't think it's HOR, but anyway, she's a geochemist, and she's now trying to do the same for the rest of the time period, for the time before the Cenozoic. So it took about 12 years for her to put this paper together. So it might take another lifetime to do the rest of the time periods. But again, what they're doing is looking at each data point, looking at what techniques were used to come up with a temperature. If it needs to be updated, they update the data point and they update based on newer ideas and models. Another guy who knows this data. In fact, he's the guy who gave me all the dots. His name is Dana Royer, Royer, and he's at Wesley.
Sure.
Uh, his stuff is really good. Uh, and then Gavin Foster's curve was okay, but it was sort of again, it's almost a decade old now. But so so those are the people whose work I trust, I guess.
Okay. I think our student Javier has looked a little into this. Did you have any questions, Javier?
Yeah, well, I looked into Gavin Foster's data, and I was kind of surprised because for a start, it is very sparse. So you get like one data point, every 1 million years, 2 million years. So basically, I mean, this is like having just a single data point for the entire Pleistocene. So I don't think we really can say that we know CO2 levels of the past. And in the periods where there are more data points, they seem to be all over the place. Like we can see about 220 million years ago in the
Right.
graph that you are displaying.
Sure.
So
Yeah. Yeah. No, I
I
agree.
think that basically one can say anything about CO2 levels. They neither support our relationship between CO2 and temperature, not discarded because the data has very bad quality.
Well, I agree with you in the sense that the older data sets are very sparse. In fact, this is actually these dots are summarized already. I mean, so each of these dots represents tens or hundreds of measurements. I asked Dana to give me the average value every million years because I was interested in the longer term trends. So there's only one dot for every million years, which may seem like a long period, and it is a long period if you're looking at this part of the curve, but for the older time periods, that's consistent with the other sorts of information we have. Uh, we have data on the order of every hundreds of thousands or millions of years, and you can just sort of see the density of the dots decreases. So back here, you might have one dot every 10 or 20 million years. So you really don't know what's going on. I left out all the dots here because there were so many dots that it would just obliterate the curve. So again, there's a problem of bias with the amount of data back through time. There's, as I pointed out, a bias that there are some times when we know it was warm, absolutely knew that it was warm, and yet all the CO2 measurements are saying it's cool. So what's going on there? Well, it turns out that these dots come from about a half a dozen different proxies. And a proxy is basically one kind of measurement or fossil or isotope or geochemical measurement that people have used to give a temperature. And there is a correlation, first order correlation, with the ones that are wrong and the proxy that's being used. So a lot of these are from, I'm trying to remember, either alkyons or soil measurements. So again, if you have two different proxies, the two proxies can give you different measurements. And what I said is, okay, we know the temperature from independently, not using CO2. We know the temperature from geological data, from oxygen isotope data. So we know this was a warm period. So these proxies are probably giving a more reasonable estimate of temperature than these proxies.
Well, you do know the temperature, but you don't know the CO2. So by selecting the CO2 level, basically you are just setting a relationship, but may not be real.
Well, I'm using the temperature to evaluate the CO2 data. So as long
So
as
you are assuming that the relationship holds over time, when really the data is not saying that.
well, you can do a statistical estimate of the CO2 and temperature, compare them statistically, and it's not a tremendous fit, but it's a better than average fit. And you can sort of just visually see it here. The way the CO2 values drop during the ice age here. This part of the curve agrees with the.
But that could just be Henry's law.
Well, I don't know, Henry, but when you have millions of data points, I think
Well,
you can begin to. Well, it's just a matter of pattern recognition, right? I mean,
no, it's a matter of correlation versus causation. Henry's law says that CO2 will come out of the oceans as they warm and will go into the oceans as they cool. So if
that's
you
perfect. I'm perfectly
don't
fine.
mind 1,000 years either way.
No, I'm perfectly fine with that. I'm not saying that CO2 causes the temperature,
Oh,
but I'm saying that they are correlated.
oh, I see.
So
Okay.
then you can decide, well, why are they correlated? Well,
Yeah.
then you have to understand the process. Uh, a warmer Earth could release more CO2.
Yeah.
And that's perfectly reasonable. The question then is, does the CO2 add anything more? Is there anything more the CO2 gives back to warming temperature? Do we have a positive feedback?
Mhm.
And but again, to me, CO2 is I am agnostic in the sense that I can figure out the temperature without using CO2, so I don't need to get involved in all the arguments about whether CO2 is causing it or being caused by it. But I can show that they're correlated. So
I
people,
see. Now, do you have another graph that just covers like the last 60 million years? It goes into a little more detail. I'd like to ask some questions about, I don't know what the name of the period is you'd call it.
Yeah, I think, let me just check. I think, no, these are all the large major time period. This one shows a little bit more detail, I think, for the last 60 million years.
You don't have more of a breakdown of the last, I'm not sure if it's.
Not prepared, not in the current set.
I want to ask what happened 33 million years ago, which
right.
maybe you can just walk us through that.
Yeah, that's this part of the curve right here. I mean, it's kind of exaggerated, but that's when we went from a hothouse, the early Cenozoic hothouse, to the late Cenozoic icehouse. So this is the drop in temperature. And what's going on here is, well, we're having, again, a lot of thermostats being set low. And in terms of the actual geology and geophysical events, the major reason, in my opinion, is the isolation of Antarctica from the world's oceans. So it becomes refrigerated, essentially. The cool temperatures can't escape through the oceans, and an ocean current surrounding it basically isolates the Antarctic waters from the more
That's
warm.
the opening of the Drake Passage.
Right.
How
And
do we know that, and what do you think happened?
well, again, we know it from our plate tectonic models because Africa and South America are separating, Antarctica and Australia and South America are separating. And it was probably somewhat complicated because continents, we have the deep ocean, but we also have continents, and continents can be flooded, so you can have shallow water flowing over the continent. So you can have shallow water pouring between two oceans while the continents are still together, and only after they separate, so there's a deep water connection, that you get the deeper currents. No, so I think it's basically there were gyres prior to the opening of the Drake Passage and the Tasman Rise, because there's two blockades, one in South America and one in Australia. And to get a through-going current, you have to open up both of them.
Both, yeah.
And the other thing that another thermostat was being set down was the India was colliding vigorously at 33 million years. So India touches Asia about 50, and then for the next 10 million years, it throws up this huge mountain range and plateau. And the idea is that things erode faster if they're higher, because there's more potential energy and gravity, and rainfall gets stopped by the mountains. So there's more erosion. And so you put back into the ocean a lot more calcium. And the calcium is a limiting factor for carbonate. So you pull more CO2 out of the atmosphere by making more calcium carbonate. Now that goes back to the correlation causation hypothesis. So I think those are two of the main factors at that time. Let me just say something about this graph, as long as it's up here. After I put together my curve, I said, well, people have said that large volcanic eruptions put a lot of CO2 in the atmosphere. And so I said, well, there should be a correlation then between the timing of large volcanic eruptions, which are called large igneous provinces, with warm periods. So I just plotted all the major eruptions, and it was like 18 out of 21 correspond with a temperature peak. Now, if there isn't a causal relation, that's kind of a weird coincidence. So again, people have argued that, yeah, this eruption, the Camp Central Atlantic Magmatic Province, caused a peak, or the Siberian traps is why we had this super hothouse in the Permo-Triassic. But there are other times where you get the eruptions and you don't have anything noticeable. Now, when I did that, I said, well, what about impacts? We knew the dinosaurs were wiped out by the Chicxulub impact, which cooled the Earth. If we plot other major impacts, how do they correlate with temperature? And the correlation isn't as good. Obviously, the best one is Chicxulub. And there's a lot more going on here in terms of the size and the nature of the eruption. But there's, you can sort of, if you have a good imagination, you can sort of see the cooling associated with the impacts. Not all of them. And then I put some ghost impacts, saying, okay, well, if we say there's a correlation, let's put some hypothetical.
Maybe.
And so the big one is, what caused this cooling event 445 million years ago? Because it's during a hothouse. And so like our cooling is not a big deal because we're in a cool period, but to have an ice age during one of the hotter periods in Earth history, something strange must have happened. So people now, I suggested an impact. I gave it the name Keone, which was the daughter of Borealis, and she's a goddess of snow. So I thought that was kind of nice. But people said that maybe the Earth had a ring like Saturn, made of busted up asteroids, or maybe there were multiple asteroid hits that put a lot of dust up. But so we don't really know, but it's an interesting anomaly on the pattern.
And Javier, when you look at these squares and circles, what do you say?
I say it, I'm just looking at, the apparent correlation. Again,
Yeah,
the curve
right.
is independent, and as a test of the curve or a test of some of these ideas, I said, oh, let's plot it up. Now, again, the precision, the peak is here, but we're, it may be millions of years off, but is that a problem of dating or, uh, and then we have peaks that we don't have impacts. I mean, known lavas for. So all I'd say it's food for thought at this point. Um, so
Let me
anyway,
ask this, let's stay on that slide. Yeah, let me ask the students if they have any questions or thoughts.
Yes, can I ask a question, Chris? Are you now reasonably confident that you understand what's driven most of the warm periods and most of the cool periods? And obviously, you're talking about the volcanic eruptions being linked to warm periods, the impacts being linked very often to cool periods. Are you of the opinion that all of these changes in temperature are linked to physical activities like that rather than changes in atmospheric composition?
well, I think it's simplistic to think that it's just CO2, and that's something that again I'm interested in the Earth system. So to explain it, CO2 could be a component, uh, but there may be a competing effect which is trying to make the Earth warmer or cooler. So all this extra CO2 doesn't have much effect. So the next slide actually addresses that question directly.
Okay.
It says, how do we make an ice house world or how do we make a hot house world? It's not one single thing like CO2, but it's the interaction of a variety of feedback mechanisms or factors. Uh, and CO2 is sort of at the center. Uh, if you decrease CO2, the idea is you make it cooler. But you can also make it cooler if you increase Earth's albedo, like snowball Earth. When the Earth was white, it reflected all the energy, so that's going to make the Earth cooler.
Yeah.
Actually, if you have more deserts, ironically, even though deserts are warm, they reflect more energy, so they can increase the albedo and make it cooler. Uh, Now, what's interesting is, and plate tectonic. So some of these are geographic effects. Some of them are plate tectonic events. Like if you collide continents, that does several things. It drops sea level because the continents are going up and the sea level is draining off of them. If you drop sea level, basically you expose more land. And guess what? Land has a higher albedo than water. So more land, so colliding continents, dropping sea level, creating more land makes the Earth cooler. So we are in a period of major continental collision. The India collision is just one part of it. There's the Alps and the Zagros, and as well as the Andes and the Rockies. Uh, so that's, I think, one of the reasons why we're in an ice house network is that it's not only CO2 is low, but there are other factors like albedo. Uh, And so each of these square boxes are sort of like a cause. More deserts, more land at the poles. If you have an impact, you can make it cooler. If you have land in the wet belts, you make it cooler. And then each of these has a flip side. So if you if you do the opposite of colliding continents, like rift continents, you have more seafloor spreading. Seafloor spreading basically causes a mountain range to occur under the ocean. That mountain pushes the water out of the ocean, so you raise sea level, and you make more shallow seas, which have a higher albedo, and you make it warmer. Also, you kill all the swamps and you flood all the land, so you stop generating coal. So that means that we're not removing as much carbon from the atmosphere, so there's more in the reservoir. Uh, and there's other things. Some of these you may recognize, like people talk a lot about melting the tundra. If you make the Earth warmer, you melt the tundra, and that releases more methane, which becomes CO2. And some of these you'll see a little symbol here, a little plus sign with an arrow, and that's meant to indicate that these are positive feedbacks. So that once you start doing it, it's like rolling a snowball downhill.
Sure.
It actually makes it worse and worse. So if we have more seafloor spreading, we raise sea level. blah, blah, blah. We warm the Earth. If we warm the Earth, we melt ice. If we melt ice, we put the water in the ocean, so we raise sea level. So this becomes a positive feedback cycle. If we make the Earth warmer, we have less ice. That means we have more land, so we decrease the albedo. That makes it warmer. So that's another positive feedback. And so that's really, I think, what's going on with global warming and climate change. It's not simply that there's more CO2, it's that CO2 can trigger some of these feedback mechanisms. Like if the CO2 makes the Earth a little bit warmer, because it does have some greenhouse effect, probably, absolute, I mean, just on its own, it's probably less than a degree. But make it a little bit warmer, you melt a little bit of the ice, you decrease the albedo a little bit, but then it begins to get caught in these positive feedbacks, and that's what causes the major effects. And of course, making it warmer melts the tundra, which puts more CO2 in the atmosphere. So here's you get your cause and effect. Is it the fact it's getting warmer and the CO2, the tundra's melting and creating CO2, or is it? It's not so much a chicken and an egg, but a positive feedback cycle, an interaction between the effects. So anyway, I'm working on this and trying to write a paper about it.
So
And but again, we could talk about this forever.
Javier?
yes, Chris, I'd like to ask you a question. I'm a big fan of your paleoclimate work. I have to say that first. I
Right.
suppose you are familiar with Thomas Westerholt paper in Science in 2020, when he analyzed both temperature and CO2 data for the last 60 million years for the Cenozoic.
Yeah,
And
I am familiar with that paper. Preceded the one that I mentioned by Hornish.
yes, and I was very surprised of the data that they presented, because if we looked at one of the figures in the supplementary information, I don't know if I can share a window, David.
Chris, can you stop sharing?
Sure. There you go.
Okay, let me see if I can. Can you see this?
Yeah.
All right.
Yeah, right.
So what we see here is that going from about 52 million years ago, in the thermal maximum of the Eocene, what we
Right.
see is that in the lower part of the graph, we can see the CO2 levels, and they were above this red line all the way down to about 28 million years ago. And then they go relatively abruptly from from a point of view of geological point of view, so that 24 million years ago they were already at around 350, 400 ppm. So this sudden drop in CO2 took place during a period in which there was a little bit of warming, from the around the mid-Oligocene cold period all the way to the mid-Miocene climate optimum. So what we're seeing here is that there's clearly no doubt that both temperature and CO2 have been decreasing for the last 50 million years, but they haven't doing it simultaneously. So we see a big drop in CO2 about 24 to 28 million years ago, at a time that was, several million years after Antarctica froze.
Right.
So,
Yeah. Well, my
well,
comment, if I may comment, the couple of things. First of all, I'd be more worried about these low values at 65 during a hothouse. Okay, so why are CO2 values so low here when we're clearly in a warm period? Also, I would be worried about, here we have a spread of values. We have some warm ones, some cool ones, but this is a very warm period. this is obviously a lot of good data. So, you know, you can't argue that CO2 levels were something like this. A lot of data, and this it's fairly consistent. I don't think there's much data relatively for this interval. So yeah, okay, there are some points below here, but yeah, it's sort of warmer here. There's some data points that are cooler. I would like to know where the data points come, what proxies they're from. As I pointed out earlier, sometimes these represent a different data source. And also, you can't argue that CO2 controls temperature by itself. You can say there's a correlation between low CO2 and low temperature, and maybe high CO2 in this case and high temperature, but we know that when we look at this curve here, this is the cooling curve caused by Antarctica, and this is the growth of the rapid ice sheet. So the Antarctic ice cap grew during the Eocene, got bigger and bigger and bigger and bigger, and then basically was established by this time. So that's what's causing the cooling. It's the Antarctic ice sheet growing, and the amount of CO2 in the atmosphere is largely irrelevant to what was going on temperature-wise. That's why, again, I don't like to look at CO2 and make direct inferences with temperature. It's more complicated. There are more things going on.
Chris, we couldn't see your cursor. You're saying the Antarctica growth happened between, was it 50 million years ago and 35?
No, about 35 and 30. You can see where that big drop off is.
Yeah, that's when Antarctica grew, extended.
Yeah, well,
yeah, that's the opening of the Drake Passage.
Yeah, Drake Passage, right. That's a better
in
way
the Tasman Sea.
Yeah, there were mountain glaciers on Antarctica during the Eocene, and so you see a little bit of cooling, but there are a number of very strong spikes, high temperatures. So you have the Drake Passage. I mean, the general curve. I mean, you have this big peak in the early Eocene, and then things look like they're cooling gradually. I would attribute that to the collision of India, and related to how it's affecting the Earth system. But then the Drake Passage opens, and we basically refrigerate the southern oceans, and then we get a little bit of warming at 15, which is interesting.
Yeah, I wanted to ask if you could tell us your version of the story of the Panama Isthmus closing.
Yeah, that's fairly recent. That's in the last couple million years. I don't have any strong story to tell except that it isolated the Atlantic and the Pacific, but it's isolating those in at the same latitude. So the water temperature there was probably about the same. So it didn't isolate cool water from warm water or anything like that. It may have affected the circulation in the Atlantic, but I just don't know enough about that particular
Didn't it have a lot to do with Greenland freezing over, or
well, Greenland seems to freeze over about 5 million years ago, so it's roughly about the same time. But yeah, we're already in an ice age. Antarctica is fully glaciated, and so it's sort of like to glaciate the northern hemisphere is harder because we have an ocean there, and water keeps the area warmer. So you have to cool it from the edges of the land and from Greenland. So, but
can you bring your slide back up of the whole 500 and something million years? I wanted to ask back. Oh, there's the gradients. Maybe you want to walk us through the gradients?
Yeah, sure. You asked about snowball Earth earlier. I really like to characterize climate, and not as a single number like the global average temperature, but as how the temperature changes from in this case, the South Pole to the equator to the North Pole. And this is called the pole to equator temperature gradient. So this dotted line that you can sort of see, I guess you can't see my pointer, or maybe you do.
We can see your pointer on your slides, yeah.
Okay, great. these dotted lines are the present day pole to temperature gradient. There are a couple of things notable. One is at the equator, it's about 26 degrees average temperature, which is in the high 70s. The other thing is that you can see that it's very flat near the equator in the tropics. The temperature doesn't change much. And that's because the way the Hadley cell circulation, basically these big cells mix everything. But then as you go towards the poles, it cools off rapidly. So by the time you get to the South or North Pole, we're about minus 30 degrees on average. But this curve has changed through time, obviously, as the Earth's temperature has changed, and it changes in two ways. Either the tropical temperature rises, and we think the maximum temperature in the tropics was about 40 degrees. And that's because there's what I call the lethal limit. Above 40 degrees, proteins begin to break down. Have you ever heard the phrase, frying an egg on the sidewalk? That's basically, so any animals living in the surface waters or on the shoreline would have a hard time, not to mention the interior of the
Yeah,
continent.
but the Earth doesn't care.
The Earth doesn't care about the animals, that's true. We don't think. The other important limit is, it's not shown here, I should have put it on that. There's 18 degrees. When the average temperature is below 18 degrees, we can form an ice cap. So if we follow any of these lower curves, as soon as it gets below 18, like this purple curve, that means that we had ice anywhere poleward of where that line intersects 18. So if we look at the modern day, if we follow the modern day curve down, it hits 18 at about this is not the average temperature. That's the exact temperature. So what I'm trying to say is that to have an ice cap, you have to have a pole temperature of minus 10 degrees. So if we look at where minus 10 degrees hits the curve, it hits it between 60 and 70 degrees. And so this is the ice limit from the pole down to about 65 degrees, 63 degrees is where there's ice. So these blue curves are all the ice ages. And if you look at the very small abbreviations here, HIA is the Hernantian, P is the Permo-Triassic, the last glacial maximum is down here. Snowball Earth is way down here. Okay, so Snowball Earth was just in its own class. The tropical temperature was minus 10 degrees. And then if you track these down, we get down to in the order of minus 80 degrees at the poles, which is interesting because minus 80 degrees is below the freezing temperature of carbon dioxide. So like on Mars has polar ice caps made of CO2 and water. The Snowball Earth had CO2 ice caps. And so you can't invoke even any warming from greenhouse gases in Snowball Earth because the CO2 is locked up as ice. But once Snowball Earth began to warm, all that CO2 would have been released. So it would have created a rapid warming back up to something more.
So I think you're saying that there is positive feedback creating Snowball Earth and
Right.
positive feedback unwinding Snowball Earth.
Correct.
What flips the switch?
Well, if Snowball Earth, again, this is a fantasy speculation. Don't take it too seriously, but we like to imagine things. At least for my book, I'm trying to imagine what the Earth was like. So if we have a Snowball Earth where most of the CO2 is being trapped under the ice, right, forming these really weird rock layers made of crystallized calcite. If you crack the ice, if you get a fissure, if the pressure of the CO2 in the ocean begins to build up and forces cracks, then the CO2 will escape. So you're trapping CO2, it's going to carbonate the oceans, but it can only carbonate so much and the gas begins to accumulate. So you could think of more of an explosive, every once in a while you get an explosive CO2 eruption. And what matters then is if this ice can heal itself, if it can anneal and close that gap. If it can't, then your Snowball Earth is going to melt away like the Wicked Witch of the West. but that's a speculation. But you can, I mean, I'm trying to make some interesting stories that have some basis of fact, but allow people to imagine how the Earth has changed in very dramatic ways during the past.
And what do we know about the evolution of Milankovitch cycles? How much more extreme was the eccentricity and so forth hundreds of millions of years ago?
Well, I think the Earth is kind of special in a sense that most of the other planets, like if you take Mars, for instance, Mars, the tilt of Mars right now is about the same as the Earth, but its tilt has widely varied through time. It has been down 60 degrees, maybe more. Whereas the Earth, we think, has conserved its tilt. And that's because we have a moon. And to change the tilt, it's based on the effects of gravity of the other planets. But for the Earth, the only gravity that the Earth cares about is that big moon orbiting that sort of locks it into its current tilt. And I think the elliptical nature of the orbit is also kind of locked in from the early solar system. I don't know that for sure, but I think that would be very hard to change because all you have to change it is the mass of the other planets. So Milankovitch cycles have always been there. We'll assume they've always been about the same, but we don't see them because, like I said earlier, they only cause a minor variation in temperature. So you have to be able to be in an ice house where you're very sensitive to all these feedbacks, where you're sensitive to a little bit cooler or a little bit warmer because the ice is going to melt and the sea level is going to change, or the tundra is going to melt or whatever. They were probably, and sometimes we see cycles in the rock record that may be Milankovitch, a little bit more salt, a little bit more silt, a little bit more mud, a little bit more carbonate. There's something called cyclic stratigraphy, which people have measured the timing of the bands, and they seem to be Milankovitch cycles, but it's just a sort of a sedimentological effect and not probably a major climatic effect.
So on the scale of tens of millions of years, what kicks off these ice ages in your view then? It's going to be tectonic, I'm guessing.
Yeah, it's again the slow changes of all the thermostats, and sort of when you're cooling the thermostat, you're changing the thermostats to cool things down. If you're in a hot house, you won't notice much, but when you start approaching some critical temperature, then it sort of snaps into a different mode.
So if you go back to your slide of 500 million years.
Sure.
Yeah.
Let's see, this is the longest one.
Yeah. So if I understand you correctly, what you're saying is that you're looking here at periods of tectonic collision and tectonic separation cycling.
Right.
Is that one of the main drivers?
Those are one of the effects. For instance, collisions cool things, right? That's the hypothesis. We're in a period of collision right now, so we're cooling. India collided, Africa's colliding. Another major period of collision was when we formed Pangaea in the late Carboniferous early Permian. So we're in a period of collision here. That puts us into this major ice age. Rifting causes warming. Pangaea broke apart starting in the mid to late Jurassic. So if you just drew a line through all the peaks, you'd see that this is a warming trend from the early Cretaceous Jurassic. So this is the breakup of Pangaea. There are other places that are colliding and rifting during this time interval. So plate tectonics is a big thermostat, I guess I would say it that way, because it controls the volume of the sea level, it controls how much land is flooded, controls the height of the mountains. But you still get, like the eruption of a tremendous amount of flood basalts every once in a while that just drives up these other peaks. So like this long-term change, tens of millions of years, and then there's maybe changes over a few millions of years related to impacts or eruptions that can drive climate on shorter cycles. That's how I would characterize it.
What do you say caused the spike at the end of the Permian?
There was as Pangaea was coming together, It was either overrode a major hotspot, or it came together in an awkward way. Not all collisions are nice and neat. There's kind of shifting and moving around a little bit, rifting. And so much of Western Siberia was rifted apart, was fractured. And out of those fractured came 3 kilometers worth of lava covering Siberia. So imagine Siberia covered by 3 kilometers of lava. That eruption released a tremendous amount of CO2. The same eruption occurred at the KT boundary in India, which preceded the impact. So the Earth was going into a little bit of a warming phase, and then the impact hit and temporarily shut off the warming phase. But then it continued into the sun as well.
Yeah. So these are the traps.
Right, the traps, right.
And the Siberian traps were back in the Permian?
Right at the Permo-Triassic boundary, exactly at the Permo-Triassic boundary. They're correlated precisely with the Great Extinction event.
Okay, amazing, fantastic. Why don't you stop sharing and we'll see if there are any other questions. Because we have scheduled another 6 hours, but we'll take a little break now.
Well, it's been my pleasure to talk about my work, and again, I'll provide David with copies of the key reprints, and if you want to read more about it. I guess a takeaway is that the Earth is a complex system, but we can sort of begin to see the big patterns because we can analyze the rock record and we can figure out the timing of things. We can begin to maybe make an attempt. My goal has always been to build a computer model, a virtual Earth that takes into account all these effects, like an Earth system model. And I thought it was impossible, except now with AI, we can probably use AI to help us build an Earth system model by both using the AI to extract all the information and then help us look for patterns. And like the conundrum is something, just because something is correlated doesn't make it causal.
Right.
On the other hand, things that are causal are often correlated. So you have to be careful, and you have to make sure you can come up with a mechanism that makes some sense. So I think so that's sort of a very long-term goal. I don't have a very long-term time left, but I'll try to get as much done as I can.
And your book you're working on now, when will that be done? And that's 3 major things.
Yeah, I've got the 3 major things figured out, at least to my satisfaction. I published the Cretaceous chapter, essentially. I got the Ordovician chapter done. So that just leaves 12 more chapters. I tell people when I get that question, I say about 18 months. And they say, 18 months? That seems really short. How are you going to get done in 18 months? And then I kind of say, well, I didn't mean 18 months from now. I mean 18 months before I die. I'll get motivated. The last 18 months are going to be pretty busy. So, of course,
all it takes to finish a book is an advance and a deadline.
Right.
And a pissed off publisher.
So the ultimate deadline. Right.
Questions from the students? Les?
Chris, your slide that showed the feedback mechanisms for the hot house and the cold house, or the ice house. I don't think I saw water vapor in there as a feedback. Surely that's a very large feedback, isn't it?
Yeah, no, that's going to be right along with rising sea level. As we get more shallow seas, we'll get more water vapor evaporating. I'm writing this up with a co-author, and he pointed that out to me, and I have to add that. But it would act in the same way as, well, water vapor is complicated because of clouds, right? So it depends where the clouds are and how high they are. So it's a struggle trying to make a diagram that's simple enough to capture some basic facts, but not try to explain everything. I developed those diagrams when I was teaching my Earth history class to try to instill that geological history isn't just a bunch of boring facts. There actually are interesting stories and interactions to tell. And you can maybe understand our history of the Earth from first principles.
Sounds like you haven't given much weight to Neershaviv's work on especially things like cloud nucleation.
I'm a little bit familiar with it. I'm very open to it. I like his periodicity thing because I saw that also. I don't know how to say this. There are some, I've been kind of saying that the Ordovician coup, the Hernantian, the one at 440, was caused by an impact. I really debated whether I should put that in the paper because I really didn't have any evidence for it. It was just a clever idea, I thought. And sometimes clever ideas can be your downfall. I remember being asked to make some maps of the future when I was a grad student, and they said they would pay me per map. So I said, great. And I said, I can make a map 50 million years in the future, no problem. Just that's how the plates are moving right now, just projected into the future. And they said, well, we'd also like 50, 100, 150, 200, and 250 million years in the future. So I went ahead and tried to speculate on how Pangea might evolve or how the continents might evolve into a new Pangea. And believe it or not, that's what people remember my work for, is this the future Pangea, which has no scientific basis at all, but it's a lot of fun to think about, I guess.
So
I'm careful about, I'm more circumspect about fun ideas that may affect my scientific reputation, but it's probably too late anyway, so it doesn't matter. But
okay, other questions?
Yes.
Les, did you have a question, or Javier?
Okay, I have a question.
sure.
Liz.
Okay, it was a fascinating talk. Thank you very much, Chris. It sounds to me as if the main thrust of your work is the history of the Earth's temperature based on your geological knowledge. What sort of confidence level do you have in that temperature curve?
Yeah,
I mean, obviously it's going to vary from, period to period.
right. In our paper, we put error bars on it. And the error bars come from the variability of the measurements. So I think, it's plus or minus a couple degrees for sure, but it's not plus or minus 10 we can tell if the Earth is in a hot house or an ice house. That's easy. It's hard to tell if the average temperature is 26 degrees or 24 degrees or 28 degrees. And especially going back in time, our confidence, our ability to make good predictions decreases. So at one point I showed two curves, one with all the wiggles and the other one with the dashed line that was sort of more smooth. I think the smooth one is really accurate. It's a good estimate. And then it's just a matter of how much variation we can really explain with the data.
Yeah, so the smooth one takes out a lot of it takes out the large peaks, doesn't it?
Right, it takes out which is, so the smooth one comes from the rocks. So rocks we know well. We know how rocks form, we know environments. The oxygen isotopes, there's it's like any scientific measurement. There are possible errors and different labs have different results. So there's always some, but we try to indicate the uncertainty on one of the graphs. I didn't show that here, but
yeah. So you would summarize that it's pretty good data that you're basing those smooth curves on anyway.
yeah, the proof is in the pudding, and that if I'm predicting a peak, a warm peak, and we find something in the rock record that says no, we have ice at the pole, then obviously that's we can always test the predictions that we make with paleotemperature with more information and more data. So and we're always improving and refining our knowledge of the Earth and its history, but geologists have been doing this for over 200 years. So we've got most of the story. The Precambrian is very difficult. I mean, I refused for a long time to say anything about the Precambrian because the uncertainties were so large. But then other people were saying some things, and I said, well, if they can do it, I can give it a shot.
Okay. Good.
Yeah. Thank you.
Les.
I agree with Leah's fascinating talk, Chris. Thank you very much. I've always been particularly interested in the CO2 part of the climate debate. And when I talk to strong proponents of man-made global warming and ask them where is the evidence that allows us to say definitely CO2 is driving the climate, they almost invariably turn to the history, to where you've been looking and say, well, geological records show it quite clearly, very clearly. What I've seen looking back in the 3 or 4 blocks of data that we have is that we repeatedly see an indication that the two go together, temperature and CO2, to an extent. But we see no evidence that it's the CO2 that's driving the temperature.
Well, I would agree. I would agree with your observation because CO2 alone can't do it. You know, if you look at the warming effect of CO2, it's about a degree. It's not very much. But that doesn't mean you can't say, well, it's not contributing much to the warming because it's not the absolute amount CO2 acts as a greenhouse gas. It's the chain of events it initiates with the little warmth. It's that whole idea of the positive feedbacks and the interaction of the Earth system. You know, and then on top of that, there's all these other effects that are completely independent of CO2, like albedo. I mean, the albedo of the Earth could care less what the CO2 is. But it's, I guess there's 2 things I'd say, is that you have to admit that it might be complex and it's not simply CO2. And also, you have to avoid the trap. I always feel that when any type of science becomes politicized, it gets ruined, basically, because people start being motivated by their political beliefs or desires, and it's especially bad for scientists because you can fall into the trap that you're more likely to get funding if you write your grant a certain way. And so I think you have to first divorce any politics out of the situation, and then before you're willing to talk about it. But I was very reluctant to talk about future global warming because I knew no matter how I approached it, how neutral I was in my approach, and how, quote, scientific or based on data, that there were going to be people who hated my interpretation and people who liked it, and it would be just a political. So I refused to publish the spreadsheet for a while because I didn't want the notoriety, and I didn't want to get involved in the political debate. But an editor came up to me and said, we have to publish this, you know. And so I'm working on a publication of that spreadsheet. So, but anyway, that's my view on.
I do find it quite intriguing when you look at if you do any sort of search on the internet for what is the evidence to demonstrate the CO2 is driving climate, almost invariably you find very knowledgeable, authoritative organizations like NOAA and the UN quoting as proof that CO2 drives temperature. They quote the historical data, and I find that quite staggering that they get away with that.
Yeah, I guess you admitted that there was a correlation, but you know, the whole conundrum is the correlation mean cause. I think in this case it does. I think CO2 does cause, but not in the simplistic, it's a greenhouse gas that makes things warmer. It's a more nuanced reason.
Thank you.
Anybody else? Javier, anything? You're muted.
Yeah. I have a graph here that maybe Chris would be interested in seeing, in which I compared one of his reconstructions, I think is a 2018 one, with those of other authors, and they are very similar, which I think gives some confidence that Chris's work is quite solid, or at least there are not data that can say very differently that how the climate changed over the past. as he says. So if you allow me to share,
Sure.
I'm
Yeah,
going
I
to,
guess while you're bringing that up, I was asked how well do I know the temperatures,
yes,
certainties, and what I've done several times is compare my result with all the other published results. And it's sort of like science by democracy, which of course is not good science, but you at least get some confidence if other people are coming up with the same ideas. So, yeah, so I know Visor and then myself.
yes. So the black curve here is your work, and it is very similar to what other authors have come with, Visor isotopes and Frake's geological evidence, and it also coincides with the ice rafting and the geological evidence from Crowley about the ice ages of the past. So I just wanted to add that.
Who is the author of that paper?
This is not a paper, this is a book, and I am the author.
Oh, okay. Great. Well, send me your reference. I'd like to read your book.
Sure.
Yeah, sure, I can send you a copy if you want.
I'd be thrilled. Thank you.
Okay.
We'll work it out.
Yeah, I apologize. I have to move on to other commitments right now, but
All right, I just have a last question. We time travel 20 years into the future and find out that Chris Scotese was wrong about one thing. It just turns out. What do you think is the most likely candidate for the one thing you might have you're maybe least certain about?
well, there's so many to choose from. Let's see. I assume it's not personal or political.
No, just of your
We're not going to own Greenland or nothing like that. No, I think it would be. It would not break my heart completely if I was wrong about the Keone impact in the ordinary. Something else.
Right.
So
okay. That was a softball.
yeah.
All right, thank you so much, Chris.
Yeah.
Really appreciate.
Thank you.
Thank you.
Really thrilled to have you, and we'll follow up and get you a copy of Javier's book.
Great, I appreciate that.
Okay, thank you. Take care. Okay, bye. All right, now everybody should know that on the 2nd of April, we have a big climate event coming. Javier, you're always welcome to any of our classes. That was less CO2 enthusiastic than I expected.
I think it's a perfect demonstration of how careful every researcher has to be about what they say about CO2.
Unless you're publishing papers about how the temperature is going to go up 6 degrees in the next 250 years.
Yes.
I didn't want to pursue that part of it because whilst admitting, as he is, that the CO2 is only a very small driver, he then actually goes to predict potentially a very large increase in temperature from the smallish increases in CO2 we're seeing. Yeah, I found it fascinating, and it's absolutely true that if you divide the history back to 540 million years into 4 blocks, the immediate past, the 800,000 years worth of ice core data, the 66 million years worth, and then the 540. In each one of those, you can see certainly 800,000 is blindly obvious. There are Milankovitch cycles, and CO2 goes up as well as temperature.
Sure.
And we all know that we've shown that for the most part, CO2 goes up after the temperature. If you go to the 66 million, it's a little more of a gradual slope for both of them. If you go to the 540 million, there are quite a few oscillations. His information there was far more accurate than I've seen before. And you could see possibly a connection between the two. But what's so frustrating is that so many organizations claim that that is absolute proof that CO2 drives climate. I just find it quite staggering that what you really see is, for a lot of the time, if the temperature is high, the CO2 level is likely to be high, but not always. So it seems you can't tell from that data which is driving which.
It's because it's motivated reasoning.
Mm.
If that didn't work, they use something else.
was very pleasant surprise with Chris there that
Yeah.
he actually confirmed what I thought, which is that you can see a relationship, you cannot tell which way around it's working.
Yeah.
I was surprised that he threw away all the data that didn't fit his beliefs.
Yes,
That was amazing.
Oh, that was a little bit.
Oh, as you pointed out, it was pretty clear that his beliefs in temperature drove his beliefs in CO2.
Yeah, yeah.
And that showed him where the signal was in CO2.
And he might be right. He might be right that the CO2 was more likely to be high during the warmer period. But because people, you can look at that and say, there, I've just proven that CO2 drives temperature, which
As Javier has shown so many times, first of all, the data is absolutely horrible. Second, it's not to be trusted. And second of all, you can't use that as a basis to throw out the data you don't like.
Classic example of cherry picking, isn't it?
I think, well, I think Javier is more clear about how little we really know about previous CO2. And I think Chris puts a little more faith into some of those that he can cherry pick from. But I think Javier has shown pretty well that all these reconstructions are pretty bad. Javier, do you know the most recent one that he talked about that was headed up by a woman?
No, I don't have that one.
I'll ask him to get us, there might be something there that we can find out.
Hornish.
Yeah, something. Yeah, I'll ask him.
Do you
Then
think,
what do you want? Do you want me to send him a link to your PDF?
As you wish, I can do it myself. I think I have his
Sure.
email, since
Good.
I corresponded with him a few times in the past. He probably
Okay.
doesn't remember.
Yeah.
I mean, I am a great admirer of his work. I think he's a great scientist, and I respect him a lot. So
Yeah.
he's just, part of the many scientists that have become convinced that all this CO2 problem is an existential crisis, which we really don't know, but probably it isn't.
Well, I just see that his main area is in the temperature record,
Yes.
isn't it? And his
Yes.
work there is exceptional and really valuable. But then he's
Yes.
compelled by the political environment to try to build a story which includes CO2 and includes.
What did everybody think about his correlation of the eruptions versus the impacts?
Well, I think it's probably, or it's difficult to say, right? I don't think that the data is also that good for that, because we're talking about millions of years. So, but I don't know if there are so many impacts that have been so significant in the past of the Earth.
Well, plus it looked like the impacts were about as regularly spaced as the eruptions.
Yeah.
That's pretty suspicious.
Mhm.
David,
Now, by the way, just to put something on that, the Earth does go through areas that have more material, regularly.
Yes.
Right. So there are periodicities to impact. So I won't say it's totally out of whack, but the fact that it kind of was seesawed back and forth with the eruptions looked a little too convenient to me.
Mm-hmm.
Les, sorry.
I got a bit confused over what he meant by impact. I thought initially he meant meteoric impact.
Yeah, he did.
Did he not actually mean impacts between continents?
No, that's different.
Okay.
That's what did he call it? Expansion and
I thought he said expansion and impact.
no, he had another word.
Collision, perhaps.
Collision.
Collision. Not impact.
The impacts were the circles. The circles were cosmic.
Meteoric.
Yeah. Yeah, that was a little suspicious to me. But also you can probably cherry pick your way through the eruption data to find those peaks as well. What do you think, Javier, about his theory about when plates are coming together? First of all, he's right. The land rises up, the seas go down all by themselves. So that makes you more vulnerable to the Milankovitch effects.
What
Land,
I
right?
think that what makes you very sensitive to Milankovitch effect is to have huge polar caps at the end, at the
Sure.
end, so
Right.
at both
Right.
poles, because then you become very sensitive to changes in the temperature gradient that can expand those areas and make the Earth much cooler, or contract them and makes it warmer. So this has been already proposed in different papers, and in fact, it is found that after Antarctica froze, Milankovitch frequencies can be better detected in climate records. So that will support the idea that it's the ice caps what makes the planet sensitive to Milankovitch.
But so you're saying that's not necessarily more land out of the water near the poles, because land out of the water near the poles will have more albedo feedback, right?
Well, the idea that tectonics and the arrangement of the continents and the making and breaking of supercontinents, it's very important for ice ages. Has been defended for a long time. There are even reviews. There are very important articles. There's one by Esper on that. So this is not something that is new or ill supported. I mean, there appears to be a certain correlation. The problem is that we have very few examples of this because there's only been 2 supercontinents in the past, and the old one was many so long ago that we don't really know much about the climate in that time. So the idea is there, and there are theories about it, but it's difficult to get enough data to support it.
I guess Chris sees it more as tectonics plates coming together and rifting apart, and Nir Shaviv sees it much more as galactic, the path of the solar system around the sun.
Yes, that's correct. There are 2 different theories, very different theories.
Yeah, right. And that's both interesting.
Yes.
Yeah, Les.
As we have Javier here, would you mind if I pose a technical question with him about molecules of gases?
I would love to have Javier come back. And
It's one simple
I know
question.
he's a busy guy, but I would like to ask if he would just come back and just hang out with us one time and talk and not have to present it. We've seen all your presentations. But if you don't mind, when you have a Wednesday evening, we'd like to invite you to just come out and talk with us.
I'll have to do it then. Okay.
Because I'm putting pressure on you under group stress.
Yes, well, after you arranged for this very interesting seminar by Chris, I'll have to repay you with a visit.
Well, we would love that. Also, next week, in case you're interested, I'll just let you know who's coming. We have Meredith Angwin next week talking about how to run a grid, electrical grid, and how not to run an electrical grid. She's fantastic, and her slides are excellent. And then we have many more interesting people. In fact, Renee Hannon will be back to talk with us about more core data, which will also be interesting, probably in a couple of months. So. And I'm also getting some nuclear energy people and others. So I'll just let you know when, but when you have a bit of a gap in your schedule, we want to invite you to come hang out with us.
Okay, sure.
Is that okay if we put it off until then, Les?
Yes.
Yeah, sure, sure.
Okay. All right. Thank you, everybody. We'll see you next week, and help me promote April 2nd. We have a big open climate event right here on April 2nd at the same time.
Can we put a bit about next Sunday? Is anybody available on Sunday to meet up with Greg?
Sunday, that's Greg Wrightstone coming to London. Who is in London and available to come on Sunday?
I'm going to be there, certainly.
Because I don't think many of us here are in London.
What time is it?
I'm overseas.
He
I'm
didn't
away.
put a time on it yet. It's a breakfast at the
Excel,
it's near to the Excel Centre.
somewhere
only
near
at,
Excel,
I'm
where
only
the
at
food is
down 20
particularly
away.
bad.
Okay.
It's a part of London where the food is terrible.
One last thing, David. I
Yeah.
just looked for that paper of Hornish,
Oh,
and it's a science paper of 2023 that is entitled "Toward a Sinusoid History of Atmospheric CO2."
oh boy.
In case anybody wants to look it up.
So you haven't seen it?
No, I didn't have it.
Well, so let
I'll
us
take a
know if
look at
that's
it.
interesting, or we'll discuss all the papers when we all get together.
All right.
Okay. Les, I don't think anybody here is available for London.
I think Michael had just said he would be. Angel, did you raise your hand as well?
Okay, thanks, Javier.
Bye.
Take care. Good night.
Yeah, I'm in London actually.
Okay, can I? I'll pass a message to David. He can email you guys with what I know, which is it'll be Sunday morning for breakfast at the hotel where he's staying at, near the, I think it's the Excel Centre, is it down near London City Airport? So it's in the Docklands area.
Yeah. You can also direct message on the platform.
Yeah, it's just not everyone watches that.
It's true, but I'm hoping not to be the switchboard.
Okay, I agree. Fine.
So, Angel, can you guys, like, you can even just put in climate community, you could just put some stuff in community there.
Yeah, great. That would be a good idea.
Or
Yeah,
in the Slack, if you, Angel, are you in the Slack for UK?
no, but I go on to the,
Yeah, in the community.
yeah.
Okay, I'll
Put an
put
announcement
all the
there.
place in the community with a hope that you can find it. If you don't get any messages from me and need to know, ask David, but I will try and do it that way. So
Yeah.
Sunday morning, probably 9:30 for breakfast with Greg.
Great. Okay. See if you can come up with a project that he would be willing to back, that people there could do and show that. But again, we need leadership. That's what's missing.
Yeah. Okay. Thanks,
So,
David.
all right. See you next week.
Cheers.
Good night. Bye.